Okay, so hello everyone. My name is Mugabe Samuel. I'm studying Masters of Science in Computer Science, and I'm going to be taking us through this study that evaluates the performance of EEG. EEG is electroencephalography, data-driven machine learning for traumatic brain injury classification. So electroencephalography, to a layman, if you're to explain it to them, it's just the study of brain activity. And in this study of brain activity, this machine is placed on someone's head, and you can see these are electrodes that are connected to the electroencephalogram that generates these signals. Later, we shall see how these signals are classified. There's gamma, beta, alpha, mu, depending on their frequencies. So we're going to be using machine learning model to tell whether a person has traumatic brain injury, or they are normal, or they have stroke. 3 classifications: traumatic brain injury, normal, or stroke. The contents of presentations are those, and I think I've already started with the introduction. So traumatic brain injury, it is mainly in the military, whereby those people after war, their war injuries, and these people have brain disorders. It is also found among civilians who get accidents and they get hit on the head. They may get also traumatic brain injury. Now, these traumatic brain injuries, they've been tried to diagnose them using CT scans, but unfortunately, CT scans are not so sensitive like the EEG. They are not able to detect mild traumatic brain injuries. So someone might be diagnosed normal, and yet they have a mild traumatic brain injury using the CT scan, which causes a problem because someone will think they are normal and hence will not go for treatment. Unlike any other disease, the earlier it's detected, the better for the person. The data we used is from the Temple University Hospital EEG Corpus Repository. I think it is one of the best databases concerning EEG data. Very reliable. And in the inclusion criteria that we used, remember we are classifying, we have 3 classes: someone with traumatic brain injuries, stroke, and another with who is normal. The age range we used is from ages of 12 to 85 in this data, and the exclusion criteria that we used is for ages from the same age range, but then if someone had let me say traumas, they had neuro problems, they had epilepsy, those ones were excluded in this data set. Move on. For the EEG data preprocessing, the data which was collected was mainly 3 minutes of wake time. The EEG machine captured this data. 3 minutes of resting state, it also captured that, and also it made sure that this stimuli, these EEG signals are stimuli free. Further, we used PopRef, it is a library in MATLib, to reduce the noise, in the signals. In feature generation, trying to generate the features that we are to use, we used phase amplitude coupling, power spectral density, spectral entropy, inter-channel cross coherency. Down here are the different ranges that I had told you about that are classified according to the signals that come from the EEG machine. Feature selection, dimensionality reduction was performed. Mainly, this dimensionality reduction is trying to reduce the dimensions of which data points are plotted. You reduce the dimensions, but keeping the originality of the vectors that still make sense to the model. It was performed and on the following methods: statistical, PCA, LDA, forward sequential feature selection, and backward sequential feature selection. Now, out of this, we got feature vectors, and the feature vectors we got from those methods, we applied them to the SVM, the support vector machine. And now, mainly in the support vector machine, if you have vectors that are close to one another, as if they are at the boundaries of a classification. For example, someone is having traumatic brain injury, as if they're having traumatic brain injury, as if they're not having traumatic brain injury, they are normal. Those vectors that are on the boundaries are what support vector machine best classifies. Now, what it does, it applies some polynomial kernels, like cubic, quadratic, it can be linear, and then it increases the dimensional space. What you cannot see in a linear dimensional space, perhaps you can be able to classify it in a cubic or higher dimensional space. Now, what was hard to classify, as someone has traumatic brain injury, someone is normal, or someone has stroke. Now, when you increase the dimensions, the dimensional space, you're able to classify this feature vector and give it to the correct class, predict the correct class accordingly. The other method that was used was k-nearest neighbors. For the k-nearest neighbors, it's mainly plotting a graph, and then this vector, this data point, it considers, for example, when you take k equals 10, it considers the 10 neighbors around. This data point considers the 10 neighbors around, and it says that if my 10 neighbors have traumatic brain injury, then this data point also has traumatic brain injury. If the most of the 10 neighbors, the highest percentage of the 10 neighbors is normal or has stroke, this data point is considered to have stroke. And if the nearest neighbors, for the 10 nearest neighbors, the highest are normal, then this data point is considered to be normal. That's mainly it for KNN. Now, for model validation, we used all these methods of model validation, sensitivity, F1 score, to check the performance of our models that we came up with. And all these models performed way better than the theoretical models. These models were able to distinguish between traumatic brain injury, stroke patients, and also the normal ones. Unlike the theoretical models, and these were outperformed They only predict normal signals and abnormal signals on the EEG. Okay. Thank you so much.